Now that we have discussed about triangles, the three-sided closed figure, now comes the new chapter number 8, called quadrilaterals. What is a quadrilateral? Let's see the discussion in brief for a quadrilateral. Before we discuss about quadrilateral, let's get into introduction of quadrilateral. Let's see the introduction. A quadrilateral, which we have as the word Quadrilateral. Lateral, the second word of quadrilateral, refers to straight line. A straight line which is straight, and then quadri, which refers to four. So a quadrilateral is a four-sided straight lines, that is a figure which is formed by four lines which form the quadrilateral. So four straight lines which enclose together to form a quadrilateral. Let's get back to the recap of a triangle. As we have seen, a triangle has three straight lines which are angular, and then the three straight lines, the line number 1, the line number 2, and the line number 3, join together to form a shape called a triangle. Three straight lines join together in this manner to form a triangle. Similarly, four straight lines join together to form a closed figure in the similar manner called a quadrilateral. So let's see how a quadrilateral is formed. Imagine I take four lines which join together to form a closed region. For example, I have line 1. This is the first line, and I take the other line and I join out here, say here. And I take the third line and I just join somewhere out here. This is line 3. And then I take the fourth line and then I join out here. So here my fourth line is joined. Therefore, each of the lines, line 1, line 2, line 3, and line 4 are joined together to form a closed figure. Such a figure obtained is called a quadrilateral. Four straight lines formed figure is called a quadrilateral. So here this is called quadrilateral. And of course, this formed by three lines as a closed region is called a triangle. Triangle, quadrilateral are how we connect through the number of sides or the number of straight lines which join to form a closed figure. Therefore, I define quadrilateral So let's see how we can define quadrilateral in words. Quadrilateral in definition: a closed region formed by joining four straight lines is called quadrilateral. Is how we define quadrilateral. Quadrilateral defines a closed region formed by joining four straight lines is called quadrilateral. The four straight lines being line 1, line 2, line 3 and line 4 closed to form a quadrilateral. Quadrilateral and its diagram. Now that we have defined a quadrilateral to be a closed region formed by joining four straight lines is what is called a quadrilateral, let's see an extended definition of understanding quadrilateral more better. There are two types of quadrilaterals which are formed. One are regular quadrilaterals and the other are irregular quadrilaterals, or ordered quadrilateral and unordered quadrilaterals. So let's see the other set of quadrilaterals which can be formed using the definition of joining four straight lines. Imagine I have four straight lines which are joined as given in the definition. As per the definition, I would like to form a closed region which is formed by joining four straight lines in this manner. Imagine I take the line 1 and I take the line 2 and I put it in this order. This is line 2. And next I have the line 3 which is arranged in this manner. Then I have the fourth line and the last line which is arranged from this point to this point, and then I have the line 4. So line 1 out here, line 2 out here, line 3 out here and line 4 out here. The four straight lines which are joined to form a closed region. So this is a closed region obtained by joining four straight lines. So let's see if this is a quadrilateral. Yes, according to the definition, this is a closed region formed by joining four straight lines, and this is a quadrilateral. We have the quadrilateral which are of two types. One, where the quadrilateral of this form is called ordered quadrilateral, and I have a quadrilateral of the form this, which is unordered quadrilateral. Therefore, a quadrilateral can be understood in two types. One is the ordered quadrilateral, which we have seen in the previous case, and secondly, it is the unordered quadrilateral, which is in this form. Unordered in the sense that they are not exactly in order, but they are cut in between. The collinearity of points is what we take into consideration in understanding this concept more better. Quadrilaterals are of two types: regular and irregular, ordered and unordered. But quadrilateral is a closed region formed by joining four straight lines. Any closed region obtained by joining four straight lines is called a quadrilateral, is how we understand the concept. Now that we have defined about quadrilateral, let's see the special features involved in quadrilateral. What are the different types of structures we see in the quadrilateral? Features. Features of a quadrilateral. So what are the features in the quadrilateral? Let's take a quadrilateral and discuss about all its features. For example, I have a quadrilateral of this four straight lines which form a closed region. Now in this quadrilateral, I have, let me denote this quadrilateral with A, B, C and D. So here the points A, B, C and D where the quadrilateral turns or where the two straight lines meet are called vertices. A is the point of intersection of this line and this line, B is the point of intersection of this line and this line, C is the point of intersection of this line and this line, and finally D is the point of intersection of this line and this line. And hence there are 4 points of intersection when the 4 straight lines form a closed region, and those points are called the vertices of the quadrilateral. So here the first thing which we understand is that features A, B, C, D are called vertices of the quadrilateral. So a quadrilateral is said to have 4 vertices A, B, C and D. A triangle has 3 vertices A, B and C. Similarly, a quadrilateral has 4 vertices A, B, C and D. Now let's see the angles. As we know that clearly the angle made by the 2 lines at A is this, and the angle made by 2 lines here is this, and the angle made by 2 lines at C is this, and the angle made by D by the 2 lines at D is this. So these 4 are called the angles of the quadrilateral. So clearly we see that there are 4 angles, 1, 2, 3 and 4. 4 angles for a quadrilateral and 4 vertices for the quadrilateral. As can be seen, angle A, angle B, angle C and angle D are called angles of the quadrilateral, and of course they are called internal angles of a quadrilateral. To be more specific, these are called internal angles of a quadrilateral. Is how we understand the vertices and the angles. The next thing is about the sides. The length of the side, the length of the straight line, the first straight line is AB, the length of the second straight line is BC, the length of the third straight line is CD, and the length of the fourth straight line is DA. So there are 4 different lengths which are taken from the straight line and then they are joined to form a closed region called a quadrilateral. Therefore, lengths are also taken into account in the quadrilateral. So along with vertices and the angles, now come the lengths. The line segment AB, the line segment BC, the line segment CD and the line segment DA are called lengths of quadrilateral. So here AB, BC, CD and DA are called the lengths of the quadrilaterals. The 4 corners or the 4 sides have the 4 different lengths of quadrilateral. They are also referred to as sides. Sometimes we refer to them as sides of quadrilateral. Is how I understand the meaning of each of these being lengths of quadrilateral or the sides of the quadrilateral. Both mean the same. Next, now that we have discussed about vertices, angles and lengths or sides of quadrilateral, now comes the discussion of diagonal, which is the most important concept in understanding the further properties of a quadrilateral. Let's see the diagonal in brief. Next is diagonal. let's see what a diagonal is for a quadrilateral. For example, the topic for the session is diagonal. What is a diagonal in a quadrilateral? Now that we have discussed about the vertices, the angles, the lengths or sides of a quadrilateral, the next important concept in the features of a quadrilateral is diagonal. So let's see the diagonal of a quadrilateral. Let me take a quadrilateral ABCD. Now we know that this is a four-sided closed region which is called a quadrilateral. So ABCD is a quadrilateral. Now interestingly, I would like to investigate on joining the two endpoints of the four-sided figure. For example, I have A and C. Let's see what happens if I join A and C or B and D. So let's try to join the 2 points, investigating the diagonals or joining the alternate sides. So A and C are called alternate points. And let me join this. I clearly see that the alternate points A and C and B and D are joined. I get a different kind of a region, the cross lines which form the diagonal. So here joining the alternate points A and C and B and D, we clearly get the line segments AC and BD. The line segments AC and BD as obtained by joining the alternate points of the quadrilateral are what are called the diagonals. So here AC and BD are called diagonals. Diagonals are the lines which are obtained when the alternate points of a quadrilateral are joined. So here when I join the alternate points, I get AC and BD, which are the diagonals. So in this case, diagonal are defined to be the line segments which are obtained when the alternate points are obtained when the alternate points of a quadrilateral join are called diagonals. Is how I understand the diagonal in a four-sided figure. Alternate points joined, I get two diagonals in the quadrilateral. Therefore, my learning outcome is that a quadrilateral has two diagonals. I make the learning outcome that a quadrilateral has two diagonals is what I understand as the learning outcome. A quadrilateral has always two diagonals. A triangle does not have diagonals because in a triangle, if I take the alternate vertices, I cannot draw a line within the triangle. But in case of quadrilateral, I can join 2 points. I can get two lines which are formed by joining the alternate points A and C and B and D. So in my quadrilateral ABCD, AC and BD are the diagonals. There are two diagonals which are formed in the quadrilateral, AC and BD. Now that we have discussed about all the possible properties in a quadrilateral, starting with vertices, sides or lengths, and the points and the diagonals, now let's see the different types of angles which are possible in the quadrilateral. Angles of a quadrilateral connected with quadrilateral. Angles of a quadrilateral. The types of angles of a quadrilateral. Let's take a quadrilateral ABCD. Quadrilateral A, B, C and D. Clearly, in the previous session, we have discussed that for a quadrilateral ABCD, there are four angles which are possible. Angle 1, angle 2, angle 3 and angle 4. So there are four angles which are possible in a quadrilateral is what we have discussed. But these angles are classified into different types with their own respective definition based on the geometrical properties. As we see angle A and B, we see that they are side by side or besides each other. But when I take angle A and C, they are not besides each other. They are apart, far apart. Therefore, I make a connection between this and this angle and make equal connection between this and this, or this and this, or this and this. So we will try to see the different types of angles which exist in a quadrilateral. Note, angle A and angle B are side by side, and when the angles are besides each other, they are called adjacent angles in the quadrilateral. Similarly, when I take A and D, I get them to be adjacent to the side AD. So they are side by side. And similarly, when I take D and C, they are side by side. Therefore, they are adjacent to each other. And similarly, C and B are adjacent to each other. So these are the four pairs of adjacent angles which are identified in the quadrilateral ABCD. So these are called adjacent angles, and they are called adjacent angles because as they are side by side in the quadrilateral, therefore these four pairs are identified to be adjacent angles or side by side angles in the quadrilateral A, B, C and D. Now let's see the outcome of these two angles. Suppose I take angle A and angle C. They are not adjacent because they are not side by side, but they are opposite to each other. So let's see what these types of angles are called in the quadrilateral ABCD. First, let me take angle A connected with angle C. Angle A and angle C are not side by side, and also the other pair possible which are not side by side are angle B and angle D. So even angle B and angle D are also not side by side. So these are given with a special name called opposite angles. And why are they called opposite angles? Because they are opposite to each other. This angle is opposite to this, and this angle is opposite to this. Therefore, angle A and angle C are opposite to each other, and angle B and angle D are opposite to each other. They are called opposite angles as they are opposite of each other. Is how we identify the opposite angles and the adjacent angles in a quadrilateral. Angle A, angle B, angle A, angle D, angle D, angle C, and angle C, angle B taken in pairs are adjacent angles in the quadrilateral ABCD as they are side by side. Next, angle A, angle C, and angle B, angle D when taken in pairs are opposite angles because clearly we see them opposite to each other. Alternate adjacent angles and opposite angles in the quadrilateral ABCD. There are 4 pairs of adjacent angles and 2 pairs of opposite angles always in the quadrilateral ABCD is the learning outcome. Now that we have discussed about quadrilateral and its geometrical properties in brief, let's see the different types of structures which have the shape of a quadrilateral. Let's investigate the different possible types of quadrilaterals through the real life objects taken into consideration. Today's session is about applications of quadrilateral. So let's investigate to search for real life models which connect with quadrilateral. Let's take different objects and see how the quadrilaterals are in different shapes out in the given situations. Quadrilateral connected with real life models. Now let's see some real life models which understand quadrilaterals in a more better manner. Imagine I take this cover of a disc or a CD. The DVD disc cover out here clearly is in the shape of a quadrilateral because I understand that there are 4 straight lines, line 1, line 2, line 3 and line 4, and the 4 lines are combined to form a closed region. So this clearly is a quadrilateral A, B, C, D. Now how do I understand this front face of the quadrilateral? It is identified that this quadrilateral is not irregular in shape but regular in shape in the manner that each of the quadrilateral corner is exactly at 90 degrees. So this is at 90, this is at 90, this is at 90 and this is at 90. Also I observe that each of the sides of the quadrilateral are equal. The length of the side out here is same as the length of the side out here, which is the same as that out here and which is the same as that out here. So all the sides are equal and each angle is 90. So I need to give some special name for this quadrilateral. So let's see the different types of real life models as we discuss. Let's go with this disc as taken out here. Then so here is what I get the shape of the disc cover when I draw on the board. So this is formed by line 1, line 2, line 3 and line 4, a 4-sided figure with special geometrical properties that each angle is 90 degrees, 90 degrees, 90 degrees and 90 degrees. And also I observe that length of each corner For example, I take the four corners as A, B, C, D. When I take a more clear picture of this, I have A, B, C, D in which my each angle is 90. As a special case, I have all the angles to be exactly L-shaped 90 degrees. And I also observe that for this model, each of the lengths are equal. That is, my length AB is equal to length BC, equal to length CD, equal to length DA. That means all my four sides are equal in length. So let's see, with each angle being 90 and all sides equal, what we can define for this kind of a quadrilateral as a special case. So interestingly, in this case, I see that for this real life model in which each angle is 90 and all sides are equal is called a square. A quadrilateral in which each angle is 90 degrees and all sides are equal is called a square. The special name I give for a quadrilateral whose first special case being that each of the corners is exactly at 90 degrees angle and that all the lengths of the sides are equal is called a quadrilateral, given by the special name square. A quadrilateral in which each corner angle is 90 degrees and the lengths of sides are equal is called a square. Square, a special case of a quadrilateral taken through the real life model of the disc cover. Cut. Now let's take another real life model to see the different quadratic shapes which are available in mathematics. The next real life model is this cardboard frame. Now here, when I see this, the first thing I investigate is that this is a closed region formed by four straight lines. Line 1, line 2, line 3 and line 4. So each of the four lines form a closed region. So definitely this is called a quadrilateral. But let's see the special features in this quadrilateral. In this case, initially when I start with angle, again here I see that each angle is 90 degrees. So every angle corner which I take out here is 90 degrees. Therefore, as in the previous case, similarly in this, I have a frame which is taken on the board. I see that the first thing I observe is this is the special feature which is observed in case of every corner being at 90 degrees. But let's see the lengths of sides. As I see that this length is shorter than this length because this length is longer when measured in length and this is shorter when measured in length. So obviously these two sides are bigger in length and these two sides are smaller in length. So the second thing what I observe is that the first thing, let me write here, angle A, angle B, angle C and angle D are all each equal to 90 is my first observation. My first observation is with each angle being 90. My second observation is that the line segments AB and CD are bigger than the line segments AD and BC, are larger lengths. These two are the larger lengths is what I observe, and these two are the smaller lengths. So my AD and BC are smaller lengths. So ABCD are larger lengths, ADBC are smaller lengths. Also, I see that when I see the frame clearly, this length seems to be exactly equal to this length because these two are 90 degrees, therefore they are parallel. So the next thing I observe is because these two are 90, these two are parallel and these two are parallel. So I see that the top line and the bottom line are parallel to each other, and the rightmost line and the leftmost line are both parallel to each other. So the third observation out here is that AB line segment is parallel to DC and AD is parallel to BC is what I observe in this case. Also, I observe that because these two are parallel and these two are parallel, I see that this length is exactly equal to this length and this length is exactly equal to this length. That is, my length here is equal to this and my length here is equal to this. So my third observation is my AB is equal to DC. The length AB equals length DC and my length AD equals length BC. Is how I get the two pairs of lengths being equal. So finally, I see that this frame has four specific geometric properties, each angle being 90, each of the angle being 90, and AB and CD are larger lengths. So AB and CD, these two are larger lengths and the other two are smaller lengths. As can be seen, this length and this length are smaller lengths. Similarly, I see that AB parallel to DC, so this is parallel to this. They have equal distances in between and these two are also equally parallel in the case. My third observation is this equals this, that is, this length on the top is same as this length on the bottom, as I can investigate through measuring tape to see if they are equal. They are equal. Therefore, this equals this and this length equally is equal to this. So these are the geometric properties I identify. Now let's see how we can connect this with the special case of a quadrilateral. So I have totally these geometric properties with each angle being 90 degrees, opposite sides being parallel to each other and opposite sides are equal, and there are two larger lengths and two smaller lengths is what we observe as the complete geometrical features. So if a quadrilateral has each angle 90 and opposite sides are equal, then such a quadrilateral is called a rectangle, a special case of a quadrilateral. So let's see a quadrilateral. A quadrilateral whose each angle is 90 and opposite sides are equal. Each angle is 90 and opposite sides are equal is called a rectangle. A quadrilateral whose each angle is 90 and opposite sides are equal is called a rectangle, a special case of a quadrilateral. All four sides equal and each angle 90 is a square, and all four sides not equal but opposite sides equal and each angle 90 is called a rectangle. Rectangle, a special case of a quadrilateral, is how we understand the special cases of a quadrilateral. Now let's see a special case of a quadrilateral called parallelogram. Now that we have discussed about square and rectangle, now comes the important definition called a parallelogram, derived from a quadrilateral. What is a parallelogram? Parallelogram. The word parallelogram itself says that a closed figure formed by parallel lines. So let's see the special case in terms of a quadrilateral. So here the word parallelogram itself has the word parallel, which means the four straight lines which are formed by forming a closed region, that is the line 1, the line 2 and the line 3, which is parallel to this. The condition is that all four straight lines which are joined together to form a quadrilateral must be parallel. The pair must be parallel, is how we understand parallelogram. The third line which I take must be parallel to the first line, and the fourth line which I take, the condition is that that fourth line must be parallel to the line 2. That means if I take out here, then this must be parallel to this, is how we understand the line 1 parallel to line 3 and line 2 parallel to line 4. All the two pairs are parallel, and thus such a line formed with a pair of parallel lines forming a closed region is called a quadrilateral, given by special name parallelogram, is how we understand parallelogram. So here I understand parallelogram to be in the shape of a rectangle, a sleeping rectangle or a slanting rectangle. In this case, ABCD is a parallelogram such that this is parallel to this, and because they are parallel, also I have noticed that the opposite sides are also equal. Let's see that in brief. Observations I make here are that in quadrilateral ABCD, my line segment AB is parallel to line segment DC, and my line segment AD is parallel to line segment BC. Is parallel to BC. Therefore, opposite sides are parallel to each other. Similarly, I notice that when two pairs of opposite lines are parallel, their lengths are equal. That is, this length equals this and this length equals this. Also, I notice the line segment AB is equal to line segment DC, and my line segment AD is equal to the line segment BC. So therefore, in this case, we see that such a quadrilateral ABCD which satisfies these two properties is called a parallelogram. Is how we understand the quadrilateral as a special case with a parallelogram. Parallelogram. Let's define parallelogram in words. A quadrilateral in which opposite sides are parallel, and of course when they are parallel they must be equal. Of course, equal in length. Is called a parallelogram. Is how we understand the parallelogram. Parallelogram, a quadrilateral in which opposite sides are parallel and the opposite sides are equal in length, is called a parallelogram. A quadrilateral with a special case of opposite sides parallel and equal is given by name parallelogram. Now let's see the angle sum property in a quadrilateral. Angle sum is today's session. As we have seen in the case of a triangle with three sides, obviously there are three angles in a triangle. The angle sum property in a triangle was defined to be that sum of three angles in a triangle equals 180 degrees. What would be the sum of all the angles in a quadrilateral is the biggest question out here. So let's investigate the sum of all the four angles in a quadrilateral. What would be the possible value of when I take all the four angles and add up? So let's take a quadrilateral ABCD. So here I have A, B, C, D, which is a four-sided closed figure quadrilateral. This is angle A, this is angle B, this is angle C, and this is angle D. So here I have four angles, angle A, angle B, angle C, and angle D. Let's sum up to see the property. So what does angle sum property define? Angle sum property. Angle sum property says my angle A plus my second angle B plus my third angle C plus my fourth angle D, which is called sum of all the four angles of a quadrilateral, which is equal to 360 degrees, is how I define angle sum property. Sum of all the four angles in a quadrilateral must equal 360. Sum of all three angles in a triangle equals 180, and sum of all four angles in a quadrilateral equals 360. Is how we define the angle sum property. Let's communicate this in words. Learning outcome here. What is that? Sum of all angles in a quadrilateral is 360. That's how I define the angle sum property. Sum of all angles in a quadrilateral inside the quadrilateral must be equal to 360 degrees. Is what we understand as the angle sum property. Now that we have discussed about the angle sum property, let's try to apply angle sum property in real life. So let's see how we can solve the problems in finding angles of a quadrilateral using the angle sum property. Applications in solving. So let's see one of the application of angle sum property in solving the math problems. For example, I have a quadrilateral where this is ABCD, a quadrilateral ABCD, in which this angle is 70 degrees, this is 80 degrees, (65 degrees). This is X. So I know three of the angles, but I want to find the fourth angle. Then my angle sum property is more significant in case of such situations. For example, for this given problem where I need to find X, let's see how we can find X using angle sum property. Clearly, we know that the given conditions are that angle A is given to be 70 degrees and my angle B is given to be 80 degrees. My angle C is given to be 65. And my angle D is given to be X. And we need to find the angle D, that is the value of X. So let's see how we can find the angle D using angle sum property. Now clearly, from angle sum property, for quadrilateral ABCD, we have angle A plus angle B plus angle C plus angle D, all sum equals 360 degrees. So angle sum property for a quadrilateral where my sum equals 360 is what we have seen in the previous session. Now that we know each of the angles, let's substitute in the given angle sum property. So here for angle A, I substitute the value of 70 as given in the problem. So here I get 70 and then my angle B, which is 80 degrees, and my angle C, which is 65 degrees, and my angle D, which is X degrees, which I need to find, is all equal to 360 degrees. Therefore, sum of all this equals 360. Now my target is to find the value of this X. So let's see how we can find X from this equation. Let me add all this 3. 70 plus 80 is 150. 150 plus 65 is 215 degrees is what we get. Plus X degrees equals 360 degrees is what we get when it is further simplified. Now because I want to find X, I put X on the left side and this is taken to the right, so that this reduces to X degrees equals 360 minus 215 degrees. Next, now 360 minus 215 is 145 is what we see. Therefore, my X is this, is what I get in terms of angle sum property. So my angle sum property, when simplified through each of the angles substituted, I get my X, that is my fourth angle, which is 145 degrees. So given the three angles in a quadrilateral ABCD, I can find the fourth or the unknown angle using angle sum property. So my learning outcome here is that the angles of a quadrilateral can be found using angle sum property. In this case, my unknown angle, angle D, is found to be 145 degrees using angle sum property. Angle sum property helps us in finding the unknown angles of the quadrilateral 145 degrees in this example problem. Now that we have discussed about the different types of quadrilaterals like a rectangle, a square and a parallelogram, let's see the different other types of quadrilaterals also existing in the branch of mathematics. Today's session is about trapezium. Let's see a special case of a quadrilateral called trapezium. Let's see what a trapezium is. Imagine I take a four-sided closed figure formed by four straight lines, such that I take one pair of straight lines to be parallel to each other. So what I do is I take line 1, which is arranged flat, horizontally flat. I take line 2, which I arrange exactly parallel to line 1. So first I arrange line 1, then I arrange line 2, which is exactly parallel to the line 1. So once I arrange in parallelity, I arrange line 3, joining the ends of first and second line. The other ends of the first and second line are joined by arranging the fourth line. So here I get a kind of a figure where one pair of lines are parallel, the other pair of lines are not parallel. So let's see what this special case of a quadrilateral is defined in mathematical sense. So when I join this, I clearly get a figure with a special case that one pair is parallel. So here I get a quadrilateral in which one pair is parallel. So ABCD is a quadrilateral with observations that AB is parallel to DC, but the lengths are not equal, only one pair is parallel. So in this case, the line segment AB is parallel to line segment DC. Such a quadrilateral in which one pair is parallel is called a trapezium. A trapezium is a quadrilateral in which one pair of sides is parallel. Let's take the definition in words. A quadrilateral whose one pair of sides is parallel is called a trapezium. A quadrilateral whose one pair of sides is parallel is called a trapezium. This being an example case of a trapezium where this line is parallel to this, but this is not parallel to this, is how we understand trapezium as a special case of a quadrilateral. Let's see the next special case of a quadrilateral in its own shape and its definition. This session is about discussion of kite. What is a kite? Now that we have discussed about a square, a rectangle, a parallelogram, a trapezium, now comes the discussion of a next special case of a quadrilateral in its own shape called a kite. Let's see the definition in brief. Imagine I take two equal straight lines and then join them out here like this. This is line 1 and this is line 2. I take two more equal straight lines and just join them from line 1 out here and then line 2 out here. So here is line 3 and here is line 4, such that this and these are equal and this are equal. Such a closed figure formed by joining four straight lines such that two equal straight lines are joined this way and the other two straight lines which are equal in length are joined this way is called a kite. The kite which I see, the flying kite. Is how I understand the shape of a kite. So here I have a kite flying and here I have a kite in quadrilateral. So such a shape is called a kite. So when I see this mathematically, I just understand that ABCD is a kite if this equals this and this equals this. AB and BC are called adjacent sides and AD and DC are called adjacent sides of the kite. These two are opposite sides and these two are adjacent because they are side by side. So if the adjacent sides are equal in a quadrilateral, Such a quadrilateral is called a kite. So here my observation are that AB equals BC. One pair of adjacent sides are AB and BC, which are equal, and the other pair of adjacent sides AD and DC are also equal. Such a quadrilateral form is called a kite. So let's see the definition of a kite. A quadrilateral whose adjacent sides are equal is called a kite. A quadrilateral with adjacent sides equal is called a kite. A special case of a quadrilateral whose adjacent sides are found to be equal. Kite as a quadrilateral. Kite as a flying kite. Now that we have discussed the different types of quadrilaterals, starting with parallelogram, trapezium, rectangle, square, kite, we have many other properties which we connect. Now comes the relation between the different types of quadrilaterals which we're going to see in this session. Initially, I would like to find a relation between a square and a rectangle. How would we understand the relation between a square and a rectangle? So today's session is about square versus rectangle. So this is about finding the possible relation between a square and a rectangle. Let's see the discussion in brief. In order that I want to find the relation between a square and a rectangle, let me take a rectangle and a square separately. Imagine I take a square and I take a rectangle. Let's see the common properties identified between a rectangle and a square. Here, in a rectangle, I see that each angle is 90 degrees, this being a square and this being a rectangle. Also in square, I identify that each angle is 90 degrees. So in both the cases, each angle of a square and a rectangle is 90 degrees. Coming to the second property, I see that in a square, all sides are equal, but in a rectangle, opposite sides are equal. So I can understand rectangle through a square because for a square, when all sides are equal, implies opposite sides are equal to each other. Therefore, all sides are equal implies opposite sides are equal to each other. Therefore, this retains the property of a rectangle. Therefore, a square with each angle being 90 and opposite sides being equal to each other can be called a rectangle. Therefore, every square is a rectangle, but every rectangle cannot be a square because all sides are not equal. We only have the opposite sides equal, but all sides are not equal, which is an essentiality for a square. Therefore, we can say that every square retains the properties of a rectangle, but every rectangle does not retain the properties of square. Therefore, every square is a rectangle, but every rectangle is not a square. Is how we understand the learning outcome. Therefore, my learning outcome is that every square is a rectangle, but every rectangle is not a square. Every square is a rectangle, but every rectangle is not a square, is the learning outcome, which makes me connect between understanding of a square and understanding of a rectangle as the special cases of a quadrilateral. Connecting square and rectangle. Is how I connect a square and a rectangle. Now next, let's see the relation between a rectangle and a parallelogram. Now that we have discussed about the relation between a square and a rectangle, where the learning outcome was that every rectangle is not a square, but every square is a rectangle. Similarly, let's investigate to search for some property connecting the trapezium, the parallelogram, and the rectangle. Parallelogram versus rectangle. So let's see the properties connected between the parallelogram and the rectangle. So here I consider a parallelogram, and in this column I consider a rectangle. Now we know that a parallelogram is in the shape of a sleeping or a slanting rectangle. Is how we understand the parallelogram. Now similarly, a rectangle is an erected property. Now let's see the properties in common. In rectangle, we have opposite sides are parallel. In parallelogram also the opposite sides are parallel. So these are the common properties identified between a rectangle and a parallelogram. Opposite sides parallel for a rectangle and opposite sides parallel even for a parallelogram. The next property is that in rectangle each angle is 90 degrees. So each angle is 90 degrees in a rectangle, but in parallelogram each angle is not 90 degrees. Therefore, I can see that opposite sides are parallel is the only condition for a parallelogram, and since in a rectangle opposite sides are parallel, irrespective of the condition that each angle is 90, every rectangle is a parallelogram. But every parallelogram is not a rectangle because it fails with each angle which must be 90 degrees. In parallelogram, each angle is not 90 degrees, but in rectangle, each angle is 90 degrees. So every rectangle is a parallelogram, but every parallelogram is not a rectangle. So let's make the learning outcome. Is how I make the learning outcome. Every rectangle is a parallelogram, but every parallelogram is not a rectangle because each angle is not 90. Is how I understand the learning outcome connecting the parallelogram and a rectangle. Similarly, if I take a square, let me introduce a square. Every square is not a rectangle, but since opposite sides are parallel, irrespective of the condition that each angle is 90, again I can say every rectangle or even a square is a parallelogram. Every square is a parallelogram, but every parallelogram is not a square. This is how I connect between a square and a parallelogram. The properties are similar to rectangle and square when connected with parallelogram. So in this manner, I can connect various properties where I can say that every parallelogram is a trapezium, or every rectangle is a trapezium, or every square is a trapezium, but every trapezium is not a parallelogram, etc. So we can interlink between two quadrilateral shapes in understanding through their common properties and the uncommon properties. So this is how we come into conclusion with various geometrical concepts like a kite connected with a parallelogram, or a kite connected with a square, or a rhombus connected with a kite. Is how we come across the different properties related to each other. Now let's see the special quadrilateral called a rhombus. As that we have already seen the definition of a kite, let's see how a rhombus is originated as a special case of a quadrilateral from the kite. Rhombus derived from a kite. Now that we have discussed about kite, let's recap the definition of a kite. So we know that a kite is a quadrilateral in which adjacent sides are equal. That is, when I take a kite, I form a kite when its adjacent sides are equal. What if I form a similar shape with all lines equal? That is, in this case, when I take the lines 1, 2, 3 and 4, I took 2 equal lengths and 2 pairs of equal lengths. What if I take all the 4 pairs of equal lengths? That is, if I have the line 1 to which there's another line 2 which is joined, and there's another line 3, and there's another line 4. That is, in a kite, this line is removed and a line of equal length is placed here, and this line is removed and there's equal line of this length put out here. Then I get this shape transformed into a shape where all lines are of equal lengths. A kite in which all the lengths are equal is called a rhombus. So this figure, when formed, is called a rhombus. A kite whose all sides are equal is called a rhombus. So here my rhombus is in the shape of a diamond. A rhombus is in the shape of a diamond with all sides equal. So I see that in this case my side AB equals my side BC equals my side CD equals side DA. So this is how I get my rhombus whose sides are equal. Let's communicate in words. A kite whose all sides are equal is called a rhombus. A kite whose all sides are equal is called a rhombus. A rhombus is a four-sided figure with all sides equal. It's the shape, looks like a diamond. A diamond in the cart. A diamond in the playing cards is a rhombus. The diamond which you see in the playing cards is a rhombus. A kite whose all sides are equal is called a rhombus, is the learning outcome I make out here. Now comes the biggest question on how we connect a rhombus with a kite. Let's see the relation between a kite and a rhombus. Rhombus versus kite. Now that we have discussed about the definitions of rhombus and kite, let's see the detailed properties and then connect through the common and uncommon properties. Here I take the case of a kite and I take the case of a rhombus. Now here I have a kite whose adjacent sides are equal, and here I have a rhombus whose all sides are equal. Therefore, this clearly satisfies that my adjacent sides out here, being this and this, are equal, and my adjacent sides out here, this and this, are equal. That is, when I take it in the form A, B, C, D, my adjacent sides AB and BC are equal, and AD and DC are equal. Therefore, I clearly understand that this satisfies the properties of a kite. But when I take the kite, its all sides are not equal. Only the pair of adjacent sides are equal. So this does not satisfy the needs of the rhombus, is how we understand the relation between a kite and a rhombus. Therefore, my learning outcome in this case is that every rhombus which has its adjacent sides equal satisfies the properties of a kite, and hence every rhombus is a kite. But otherwise, every kite is not a rhombus, because all sides of a kite are not equal, and hence it is not a rhombus. So my learning outcome comes out to be every rhombus is a kite, but every kite is not, or I can say a rhombus is a kite, but a kite is not a rhombus, is how I understand the relation between rhombus and kite. A rhombus is a kite, but a kite is not a rhombus, is how the learning outcome relates a rhombus and a kite. Now that we have discussed about the different types of special cases of the quadrilateral, let's take the case of parallelogram and define its various mathematical properties connecting the parallelogram. A special case of a quadrilateral called parallelogram. Today's session is about properties of a parallelogram. Properties of parallelogram. One of the most important property is the property which connects the diagonal of a parallelogram. So let's see and revisit a parallelogram and its diagonal. We know that this is the shape of a parallelogram. A, B, C, and D, in which opposite sides are parallel, is how we understand a parallelogram ABCD. Now, the property which connects the parallelogram is with the diagonal. So imagine I connect the diagonal AC. Now here AC is the diagonal which connects the two alternate points. Now when we see clearly the parallelogram with AC being the diagonal, the significance of the diagonal is that this diagonal cuts the parallelogram into two triangles. So here I have diagonal AC cuts the parallelogram ABCD into triangles, the two parts being the shapes of triangles. The first part of the diagonal is triangle ADC, and the other part of the triangle of the other part of the parallelogram cut by the diagonal is ABC, triangle ABC. Therefore, I have two triangles as cut by the diagonal AC, such that ABC is one triangle and ADC is the other triangle. The two triangles, triangle ADC and triangle ABC. So let's see the properties connecting these two triangles in a parallelogram. So here the property states that a diagonal cuts the parallelogram into two equal triangles, or if the diagonal cuts the parallelogram, then the two triangles formed are said to be congruent to each other. That is, the property is triangle ABC is congruent to triangle ADC. Is how we connect the property. When two triangles are formed by the diagonal, the two triangles are congruent, always in a parallelogram. Let's take the other case. If suppose I have another diagonal which joins from D to B. Now again I have triangle also for diagonal BD. Out here I have two triangles ADB and BDC which are also congruent to each other. If I take the diagonal, the second diagonal, triangle ABD is also said to be congruent to triangle BDC. Is how we understand the property of a parallelogram. A diagonal cutting the parallelogram cuts the parallelogram into two triangles, and the property says that for a parallelogram where the diagonal cuts the parallelogram into two triangles, the two triangles must be congruent to each other. This congruent to this and this congruent to this. There are two diagonals in a quadrilateral, diagonal 1 and diagonal 2. This diagonal makes these two triangles congruent. This diagonal makes these two triangles congruent, and this diagonal makes these two triangles congruent. The diagonal connects with congruency of triangles. Now let's see the property of a parallelogram which connects with the sides. Let's see the other property of a parallelogram. Connecting with its sides. So let's see the property which connects with sides. Parallelogram ABCD. Here is the parallelogram A, B, C and D. So clearly in a parallelogram we know that opposite sides are parallel. Now when the opposite sides are parallel, clearly I see that there is equal distance between the two parallel lines. But this equal distance is again cut short by two more parallel lines, where again there is an equal distance between these two parallel lines. So parallelogram is a closed region bounded between the pair of parallel lines. Therefore, it comes to an interesting geometrical property which arises out here. The pair of parallel lines makes a bounded region where the lengths are equal. The pair of parallel lines always makes the lines to be equal. So this side must be equal to this, and this side must be equal to this. That is, when the opposite pairs are parallel in a quadrilateral, their opposite sides are equal or also equal in a quadrilateral. Therefore, with this property, I come to a conclusion that the opposite sides AB is equal to DC and my AD equal to BC. Therefore, my opposite sides are equal. So here, the reason being that since opposite sides are parallel. Therefore, the opposite sides must be equal. Therefore, the property in a parallelogram is that learning outcome in this property is that opposite sides of a parallelogram are equal, is how I understand opposite sides of a parallelogram are always equal. Property number 2, opposite sides of a parallelogram are always equal. Now let's see the converse of the property which we have discussed in the previous session. Like for example, I have taken a parallelogram in which opposite sides are parallel, then that quadrilateral has its opposite sides equal. Now let's take a quadrilateral in which the pair of opposite sides are equal. Then will that be a parallelogram? So here it is converse of parallelogram. So let's see the converse as the properties of a parallelogram. The converse says if a pair of opposite sides of a quadrilateral are equal, then the quadrilateral must be a parallelogram. Then that quadrilateral must be a parallelogram, is how I understand the converse. That is, if I take the pair of opposite sides, I take the two lines of equal lengths and I take two pairs of equal lines and I form a closed figure, then that closed figure must be the shape of a parallelogram, is how the property defines. So the four lines, these two being of equal length and these two being of equal length, clearly I get a closed figure in which the opposite pairs being equal makes it indirectly to be parallel, is how we understand as the converse of the previous session. If two equal lengths are paired together to form a four-sided closed region, then mathematically we conclude that those pairs will obviously be parallel. So the parallelity derived from equal lengths is how the learning outcome comes out. Therefore, in this case, opposite pairs equal, opposite pairs equal implies opposite pairs parallel. So equality implies parallelity and parallelity implies equality. So opposite pairs equal implies opposite pairs parallel. Hence, a parallelogram is how we understand a quadrilateral reducing to a parallelogram, either the pair of sides being equal or the pair of lines being parallel. Parallelity implies equality and equality implies parallelity. If a pair of opposite sides of a quadrilateral are equal, then that quadrilateral must be a parallelogram. The converse of the previous session. Now next, let's see the other properties involved with parallelogram. Now that we have connected between parallelity and equality of opposite sides in a quadrilateral reducing to a parallelogram, let's connect with angles. What are the properties related to angles in a parallelogram? Angle properties. In a parallelogram. So let's see how the angle properties are defined in a parallelogram. So let's take a parallelogram ABCD. So here I have a parallelogram A, B, C, D. So A, B, C, D is a parallelogram in which opposite sides are parallel and of course equal. Now this is angle A, this is angle B, this is angle C, this is angle D. Now here A and C are called opposite angles, B and D are called opposite angles. Angle A, angle C, angle B and angle D are called pair of opposite angles, are referred as pair of opposite angles. So let's see in today's session about the property which connects with opposite angles in a parallelogram. For a parallelogram ABCD, the property says that opposite angles of a parallelogram are always equal. That is, this equals this and this equals this. So the property here says that opposite angles in a parallelogram are always equal. Opposite angles in a parallelogram are always equal. Is how we conclude the property. That is, in this case, angle A must be equal to angle C and angle B opposite to that is angle D must be equal if ABCD is a parallelogram. For a parallelogram ABCD, opposite angles must be equal is how we understand the property connecting the opposite angles. Opposite angles in a parallelogram are always equal. Now let's see the converse of the previous session. Today's session is about the converse connected with the angle properties in a parallelogram. The converse. So what is the converse of the angle property? Let's revisit the angle property as discussed in the previous session. In a parallelogram ABCD, if we have defined that the opposite angles are equal. Now comes the question, if in a quadrilateral the opposite angles are equal, will that be a parallelogram? is how we understand the converse. So imagine I take a quadrilateral ABCD, which is not a parallelogram yet. I say my opposite angles, angle A and angle C, are equal, and my other set of opposite angles are equal. Then this quadrilateral must form a parallelogram, is how the property defines. If the opposite angles in the quadrilateral ABCD are equal, then the four-sided closed figure formed, the quadrilateral thus formed with opposite angles being equal, must be a parallelogram, is how we understand the converse of the angle properties. So this equals this and this equals this. So the property says if opposite angles are equal in a quadrilateral, then the quadrilateral will form a parallelogram, is how I understand the property connecting the parallelogram with opposite angles. So if opposite angles are equal in a quadrilateral, then the quadrilateral will form a parallelogram. Therefore, for quadrilateral ABCD, which we have out here, if angle A equals angle C and angle B equals angle D, that is opposite angles are equal, then ABCD is a parallelogram. That is, ABCD will automatically have its opposite sides being parallel. With opposite angles equal, the quadrilateral shifts to be a parallelogram, is how we understand the learning outcome of the converse of angle properties in a parallelogram. Now that we have discussed about the angle properties in a parallelogram, now comes the question on how do we connect the properties of a parallelogram connected with its diagonals. Today's session is about the diagonals of a parallelogram connected with its own respective properties. Properties connecting the diagonal. Diagonal properties in parallelogram. Let's consider a parallelogram with its respective diagonals. So here I have a parallelogram A, B, C and D. So clearly we know that the opposite sides are parallel and of course equal. For this parallelogram we have two diagonals as discussed in the previous session. So one of the diagonal is obtained by joining AC and the other diagonal is obtained when I join BD. So here my diagonals are AC and BD are the diagonals. Now let's see what is the property which connects these two diagonals. Before this, I clearly understand that diagonal AC intersects diagonal BD at say some point M. So I clearly have a point of intersection of the two diagonals as represented by M. So here my M is the point of intersection of the two diagonals. So M is the point of intersection of the two diagonals, diagonal AC and diagonal BD. So let's see the property connecting the diagonal property. The property says that the diagonals AC and BD bisect each other in a parallelogram. This is one of the most important property in the parallelograms because bisecting concept helps us in solving many mathematical problems. To come with the property, diagonals bisect each other in a parallelogram. What do we mean by bisect? The word bisect means cutting at midpoint. That means the diagonal AC, say the midpoint or the middle point exactly of the distance A and C is M, then clearly the middle point of BD is also said to be M. It's how we understand bisecting each other. Bisecting each other in the sense the midpoint of AC must be the same as the midpoint of the other diagonal BD. So therefore, when the point of intersection is this, I understand this equals this and this equals this. Is how the bisection is understood in parallelogram concept. Diagonals bisect each other in a parallelogram. Therefore, AC and BD bisect at point M. That is, M is the common midpoint for the diagonal AC and the diagonal BD. Is how we understand the bisection. And using this property, M bisects AC and BD. That is, more simpler understanding, M is the common midpoint for the diagonals AC and BD. Is how we understand the diagonals bisecting each other. Diagonal property, diagonals in a parallelogram bisect each other, is how we understand through the parallelogram A, B, C, D. Now that we have discussed about the diagonal property in a parallelogram, now comes the discussion of converse. Will the converse be true? That is, if the diagonals in a quadrilateral bisect each other, will the quadrilateral form a parallelogram? It's the biggest question in converse. So let's investigate the converse of the session. Diagonal property. Parallelogram converse. So let's see the converse of the previous session. Imagine I take a quadrilateral A, B, C and D. So I have a quadrilateral formed by four lines in the closed region A, B, C and D. Let's see the property connecting the converse. Now imagine I take the two lines joining AC and BD out here. Now, if the diagonals bisect, that is, if the diagonals meet at the common midpoint, then will this shape be a parallelogram? Yes, it will be. That is, the converse holds for a quadrilateral where the diagonals bisect each other. So let's see the statement of converse. The converse statement says, if the diagonals of a quadrilateral bisect each other, then the quadrilateral will form a parallelogram. Yes, the converse of the previous session holds. If the diagonals of a quadrilateral bisect each other, then the quadrilateral must form a parallelogram. They must form the pair of lines which are parallel to each other, is how I understand the converse of the previous session. Therefore, in this case, M bisects the diagonals AC and BD, implies M is the common midpoint of the diagonals AC and BD, and that implies quadrilateral ABCD reduces or forms a pair of parallel lines. Quadrilateral ABCD forms a pair of parallel lines, this being parallel to this and this being parallel to this. Therefore, quadrilateral ABCD is now called a parallelogram. Now I can call my quadrilateral ABCD to be a parallelogram. Therefore, the converse, if the diagonals of a quadrilateral bisect each other, then the quadrilateral must be a parallelogram, is how we understand the concept connecting the converse. Now that we have defined about the quadrilateral and its different types of quadrilaterals, the most important of them being parallelogram, and various other quadrilaterals like square, rectangle, trapezium, rhombus, kite, etc. The most specific quadrilateral which we have discussed in the previous session and its varied properties was parallelogram. So let's see the other definition of how a quadrilateral can be defined to be a parallelogram, or how a parallelogram is defined, or when the quadrilateral becomes a parallelogram. So these are related to the property, another condition for quadrilateral to be a parallelogram. Other condition for a quadrilateral to be a parallelogram. So let's see the other condition. Now that we have defined the quadrilateral to be a parallelogram, if its opposite base, or if the pair of sides of the opposite sides are parallel, then the quadrilateral becomes a parallelogram. Now let's define the other condition for a quadrilateral to become a parallelogram. So coming out with the definition, when the opposite sides are parallel, is how we have taken for line 1, line 2, line 3 and line 4 arranged in such a manner that it forms a closed region with its opposite base being equal, is said to be a parallelogram. Now we will try to change the definition into a more modified form. Let's see the definition, which stands for another condition for a quadrilateral to be a parallelogram. A quadrilateral definition. A quadrilateral is said to be a parallelogram if its opposite sides are parallel and equal. This is said to be the modified form of defining a quadrilateral to be a parallelogram. So a closed four-sided figure that is a quadrilateral is said to be a parallelogram if its opposite sides are both parallel and equal, is how we can combine the parallelity and equality for making a parallelogram or defining a parallelogram. So ABCD is a parallelogram if quadrilateral ABCD is a parallelogram if AB is parallel to DC, and AD parallel to BC. AD parallel to BC. Along with this, it must also satisfy the equality condition. This becomes parallelity condition, and the equality condition is that AB must be equal to DC and AD equals BC. Is how I understand a quadrilateral ABCD reducing to a parallelogram if it satisfies the parallelity condition. Parallelity and equality condition is how I understand a quadrilateral reducing to a parallelogram as another condition for a quadrilateral to be a parallelogram. The quadrilateral is said to be a parallelogram if its opposite sides are parallel and equal. That's how we understand the definition for quadrilateral reducing to a parallelogram. Now that we have defined a parallelogram and a rectangle as the special cases of the quadrilateral, let's see how a rectangle can be derived from a parallelogram. There's an interesting property which connects deriving a rectangle from a given parallelogram. Today's session is about deriving a rectangle out of the parallelogram. So let's take a parallelogram ABCD. Deriving rectangle, deriving a rectangle from a parallelogram. So let's see how a rectangle is derived from a parallelogram ABCD. So here is the parallelogram ABCD. Of course, the pair of sides being parallel and equal. Now, the two sides are parallel and opposite sides are equal. Now let's see how a rectangle is derived. Now as I have four angles, angle A, angle B, angle C and angle D. Now here I would like to draw a bisector for each angle. That is, for angle A, I take the bisector that is exactly at equal angle. I just extend this. Similarly, I take the bisector of angle D. Angle B. So here is the bisector of angle B, exactly cutting at equal angle. So here is the bisector for angle B and here is the bisector for angle A. Similarly, I have a bisector for D which I derive out here, and a bisector at C derived out here. So I have taken for each angle of a parallelogram a bisector, that is a line which makes equal angles on either side is what we call the bisector. So here I take a line which makes equal angles on either side. I take another line which makes equal angles on the other side, similarly at C and D. Interestingly, I see that each of the lines, line 1 and here is line 2 and here is line 3 and here is line 4. So these four lines try to intersect at four different points and it forms a region which is this. It forms a region which let me denote by PQRS. Now this region seems to look like a four-sided closed figure. Yes, the four lines, line 1, line 2, line 3 and line 4 intersect to form a four-sided closed region, and which is called a rectangle. The bisectors of a parallelogram intersect to form a rectangle. It will have each angle is 90 and opposite sides are equal, is how I see the property for this. So PQRS quadrilateral PQRS, which is formed by the bisectors of the original parallelogram. Usually this quadrilateral is formed by the bisectors of each of the angle of the parallelogram, which is formed by the bisectors of each vertex A, B, C, D. Each vertex of the parallelogram ABCD is a rectangle. is how I understand the property. The quadrilateral PQRS, which is formed by the bisector 1, bisector 2, bisector 3 and bisector 4, forms a close-sided region which is called a rectangle. Is how the property comes. Therefore, PQRS is a rectangle and each of the angles is 90 and opposite sides are equal. Is how we understand the concept of the rectangle derived from a parallelogram. So any parallelogram whose bisectors are meet at 4 different points, that 4 close-sided region is called a rectangle. This holds for any parallelogram existing in the branch of mathematics. Rectangle derived from a parallelogram. Now that we have discussed about triangles and quadrilaterals with their varied properties, now comes the most important theorem in the topic of quadrilaterals or in the topic of triangles, called Midpoint Theorem. So let's see what a midpoint theorem is. Midpoint Theorem. So what is a midpoint theorem? As a theorem itself clearly says midpoint, therefore I see that this theorem is related to a midpoint taken on a line segment. We all know what a midpoint is. Just to recap, if I take a line segment AB, then exactly the middle point, which is exactly in the middle of A and B, is called midpoint. So in case of this line segment, this equals this and M is called midpoint of line segment AB. Is how we understand the midpoint of a line AB. Here is M, exactly in the middle. So let's see the midpoint theorem in brief. So let's derive the statement before we come to the understanding of midpoint theorem. The statement. The statement says the line joining the midpoints of any two sides, the line joining the midpoints of any two sides of a triangle is parallel to the third side. Is how we define a midpoint theorem. So midpoint theorem states the line joining the midpoints of any two sides of a triangle is parallel to the third side. So let's see the statement in brief. Now this whole theorem is related to a triangle. So let me take a triangle ABC. So here is the triangle A, B and C. Now the theorem says the line joining the midpoints of any two sides of a triangle. So let me take the midpoints of any two sides and then connect the two midpoints so that I get a line. Is how I understand the first part of the statement of the theorem. So here let me take the midpoint of AB, which is say denoted by D, and let me take the midpoint of AC at E. Just like the midpoint of AB here is M, which is exactly in the middle, same way D is exactly in the middle of AB and the point E is exactly in the middle of AC. Now let me join the line D. So I have a line segment connecting the two midpoints D and E. So the line referred here is nothing but the line DE in the diagram of triangle ABC. Now it says that the line which joins the midpoints of any two sides of a triangle, in this case being DE, is parallel to the third side. Midpoint theorem says such a line which exists connecting the two midpoints must be parallel to the third side. Is how we understand the midpoint theorem. So midpoint theorem connected with two midpoint lines are parallel to the third side. So here DE is parallel to BC. Let D be midpoint of AB and E be midpoint of AC. Of AC. Now the next step is that I join DE. So once I get DE, now the midpoint theorem says midpoint theorem says that DE is parallel to BC. Is how I understand the midpoint theorem. The line joining the midpoints of any two sides of a triangle is parallel to the third side. It need not be the midpoints of these two sides. If I take the midpoints of these two sides, then that line must be parallel to this. If I take the midpoints of these two sides, then the line joining the midpoints must be parallel to this side. Is how I understand through the statement of midpoint theorem. Midpoint theorem connects the parallel lines with the midpoint concept. Now that we have defined the midpoint theorem connected with the parallelity of the two midpoints joined for the two sides of a triangle, now let's see the extension of the midpoint theorem. There is an extended property which relates to the midpoint theorem. So let's see the extension of midpoint theorem. Extension. So the extension of midpoint theorem says that, before that, let's recap with the midpoint theorem. Now the midpoint theorem says if I take a triangle A, B, C and I connect the midpoints, midpoint of AB being D and midpoint of AC being E, then the line which joins the two midpoints, we know that it is parallel to this. That's how we have understood midpoint theorem in the previous session. Now with this parallelity, let's see the extension property of midpoint theorem. So along with DE being parallel to BC, by midpoint theorem, DE is parallel to BC. But the extension property says that the length DE will exactly be half of the length of the third side BC. So let's see the extension mathematically. Extension of midpoint theorem says that length of the line segment DE is exactly half of the length of its third side, which is BC. So this length must be half of this. If this is 12 centimeters, this must be 6 centimeters. If this is 7 centimeters, this must be 3.5 centimeters. Is how we understand the midpoint theorem connected with the extension. So here simply I can write this as DE is half BC, or I can also write this as BC is twice of DE. Is how I understand the extension. So my theorem for extension says if a line joining the midpoints of two sides of a triangle is parallel to third side and also is exactly half of the third side. So my statement goes like this. The line joining the midpoints of any two sides the line joining the midpoints of any two sides of a triangle is parallel to the third side and exactly half of it. This is what defines the extension of the midpoint theorem. So now proudly I can define or state the midpoint theorem as the line joining the midpoints of any two sides of a triangle is parallel to the third side and exactly half of it. Is how we can relate the midpoint theorem completely in its own understanding. So the statement is how we define midpoint theorem and its extension connected with midpoints and parallelity. Now that we have discussed about the midpoint theorem and its extension connected with parallelity and the midpoints, let's see if the converse of the same theorem holds. So let's see today's session about converse of midpoint theorem. That is, if the line passes through the midpoint and is parallel to the third side, will the other point be also the midpoint, or will the other point bisect the third side? Is how we understand the converse. That is, a line which passes through one of the midpoint and parallel to the third side, when it cuts the other side, will this cut the midpoint? Is how we have to understand the converse. So we are investigating if this line passing through the midpoint of this side and parallel to the third side passes through the midpoint, exactly passes through the midpoint of the other side, or if it passes through the other point, is what we are going to investigate in the converse of midpoint theorem. Converse of the midpoint theorem with its statement. Converse of midpoint theorem. So let's make the statement. The line passing through the midpoint of one side of a triangle. So a line passing through midpoint of one side of a triangle. Midpoint of one side of a triangle. And which is parallel, which is parallel to the other side. And which is parallel to the other side. Must bisect the third side. That is, this comes out to be the third side. And this line, which is parallel, must pass through the midpoint of the third side. There's no other way. the line cannot escape the midpoint, is how the converse states. And which is parallel to the other side must bisect or must pass through the midpoint. The third side. That is, it must pass through the midpoint of the third side. No escape. Is how we understand the midpoint theorem. So let's see the midpoint theorem in its converse. ABC is a triangle. Let D be the midpoint of AB. Then a line which passes through this midpoint and which is parallel to the third side. So here, let D be midpoint of AB. And let me extend this line to be some F, and DF parallel to BC. Then in this case, then Converse of Midpoint Theorem states that the converse of midpoint theorem under these two conditions states that DF passes through the midpoint. So this is the midpoint E of AC. Then the converse of midpoint theorem states that the line DF or the ray DF passes through the midpoint E of AC. Is how I understand the midpoint theorem in its converse. Converse of midpoint theorem, which says the ray passes through the midpoint. So we have both the midpoint theorem and its converse both being equally true. That is, when a line passes through two midpoints out here, then that line must be parallel to the third side, and in case the line passes through one of the midpoint and is parallel to the third side, also that line obviously must pass through the other midpoint. Is how the midpoint theorem and the converse of midpoint theorem both hold equally true in the branch of mathematics. Midpoint theorem and converse of midpoint theorem. Now that we have discussed about the midpoint theorem and its converse, now the question comes on applications of midpoint theorem. So today's session is about applications of midpoint theorem in the branch of mathematics in solving of math problems. So let's see the applications in brief. Applications. So let's see the applications of midpoint theorem. Here I have a question which says, find the area of the following triangle whose altitude is 4 centimeters. Now here I have a question which says about finding the area of the triangle whose altitude or the height is given to be 4 centimeters. So let's take the triangle. Here is the given triangle. The question says D is the midpoint and E is the midpoint and ABC is a triangle such that the distance between AB is, say my altitude is, let me take 12 centimeters and this be 4 centimeters. That's how, or I take this to be 5 centimeters is what is given. Now my question is about finding area of this complete triangle. So let's see how I can find area of this triangle using the concept of midpoint theorem. Midpoint theorem and its application in solving math problems. So let's take the given information. Now altitude is given to be 12 centimeter, that is my altitude which drops as perpendicular from here. Let me take this to be AL. My altitude is the perpendicular or the height in the triangle. My AL in triangle ABC, the given things are the altitude AL is given to be 12 centimeters and my DE, the distance between midpoints, DE, distance between midpoints, DE is given to be 5 centimeters. And the question is about finding the area of this triangle. So I have my base, I have my height, but the dimensions of the height is given to be 5 centimeters, but the dimensions of the base are not given. So my target out here is to find the dimensions of the base, that is the length BC of the triangle ABC. So how do I find the dimensions of the base? Let's see how we can do using midpoint theorem. Now here, by using midpoint theorem, in my triangle ABC, my BC is twice of DE, or I have my BC is twice of DE. This is strictly from the extension of the midpoint theorem, as we have seen in the previous session. So when the line joins the midpoints of two sides of triangle, then this is exactly half of this, and of course parallel to this. Is how we have seen the midpoint theorem in a statement. Therefore, my BC is twice of DE, which is already given to be 5 centimeters. So DE equals 5 centimeters is substituted in place of DE. So which comes out to be 10 centimeters. Therefore, I have my length of BC, which is 10 centimeters. My BC is 10 and my AL is 5. So let's utilize. Therefore, length of BC is 10 centimeters and length of AL is 12 centimeters as given in the question. The altitude is 12 centimeters. Therefore, in order to find area of triangle, we know that area of triangle is half into base into height. Therefore, my base is this and my height is this. So this is the base and this is the height. And therefore, area of triangle ABC would be half times base times height. Therefore, using the formula for area of triangle ABC is half times base times height. Half into base into height. In this case, half times my base is 10 and my height is 12, which on further simplification gives 12 5s, 2 1s, 2 5s, 12 5 60 centimeters square. Therefore, area of triangle ABC, whose altitude is 12 centimeters and the distance between the midpoints D and E is 5 centimeters, is on the whole 60 centimeter square. Is how I can find the area using the midpoint theorem. Given the altitude and the distance between midpoints, I can find the length or the dimension of the third side using the midpoint distance, using the midpoint theorem and its extension. So midpoint theorem helps us in finding base and height, and hence the area, which is 60 centimeter square. Area of triangle found using midpoint theorem. Applications of midpoint theorem in finding areas of triangles.